Walk outside on a clear night and the sky can feel finished. The stars look like fixed points. The dark between them looks empty, and distance feels like the only real barrier between us and whatever lies beyond. But that picture is wrong in a deeper way than most of us realize, because the oldest parts of the universe are not hidden simply by remoteness. They are hidden because the light they sent out no longer arrives here looking like itself. It has been stretched, slowed into longer wavelengths, pulled out of the visible world and into infrared, until the early universe stops being a matter of better eyesight and becomes a matter of learning how to see altered light at all. If you enjoy long journeys like this, stay with me. And if this kind of grounded deep space storytelling is your thing, subscribing is a quiet way to keep these coming. Now, let's begin with something that feels almost too ordinary to question. We grow up trusting light. You open a curtain, and the room appears. You look across a street, and color seems immediate and honest. Even when we learn that stars are far away, we usually keep the basic intuition that sight is simple. Light leaves an object, crosses space, reaches our eyes. The deeper the darkness, the stronger the telescope you need. That feels reasonable. For nearby things, it mostly works. The trouble begins when space itself refuses to stay still. When astronomers say the universe is expanding, it is easy to picture galaxies moving away from one another like sparks from an explosion. That image is useful up to a point, but it misses something that matters here more than almost anything else. The universe is not just carrying galaxies farther apart, it is stretching the space through which light travels. And when light crosses expanding space for long enough, its wavelength gets stretched with it. That changes everything. A beam that began its life as visible light can arrive as infrared. Features that would once have looked in their own galaxy, more like ordinary optical glow, no longer reach us in a form human eyes can detect. It is a little like hearing a siren sink lower and lower in pitch as it moves away. Except this is not sound in air. It is light crossing billions of years of expanding reality. The message is still there, but its shape has changed on the way. So the great challenge of deep cosmology is not only to collect faint light, it is to catch light that has been transformed. That is why the James Webb Space Telescope matters in a way that goes beyond the usual language of it being stronger, sharper, or more powerful than what came before. Those descriptions are true, but they are not the heart of it. Webb was built for a universe whose oldest messages no longer arrive in visible colors. It was built to meet ancient light where that light has migrated. You can feel the difference most clearly when you compare it to the telescope that defined the previous age of deep space imagery. Hubble changed our sense of the cosmos. It reached from ultraviolet into a modest slice of near-infrared, and it gave humanity some of the most important images ever taken. But as we push deeper toward cosmic dawn, there comes a point where the useful features of early galaxies keep sliding redward, past the range where older observatories could follow them properly. It is not that the universe suddenly stops. It is that its oldest pages drift out of one library and into another. Webb was built with that drift in mind. Its mirror spans 6.5 meters, large enough to collect vastly more light than Hubble. Its instruments cover a range from roughly the red edge of visible light well out into the mid-infrared. And then there is the cold. That part is easy to treat as engineering trivia until you realize what heat means for an infrared observatory. Everything warm glows. A telescope trying to detect faint infrared light while bathing in its own heat would be like trying to spot fireflies through a floodlight pointed back into your face. So Webb hides behind a giant sunshield and lives in deep cold. One of its instruments, MIRI, is cooled even further, down to temperatures so extreme they barely belong to everyday experience. This is not drama. This is discipline. To see the oldest stretched light, the telescope has to become quieter than almost anything we build. And once you understand that, the title starts to sharpen. James Webb just recorded infrared light beyond previous limits is not really a story about a single heroic image. It is a story about a threshold, about what happens when the oldest visible fingerprints of distant galaxies have been stretched so far that even near-infrared is no longer the whole answer. To keep following them, you have to move deeper into infrared than earlier astronomy could usefully reach for this purpose. That threshold has now been crossed in a way that changes the feel of the field. One of the clearest examples is a galaxy known as JADES-GS-Z14-0, The name is technical, but the reality behind it is not. We are seeing this object as it was less than 300 million years after the Big Bang. Sit with that for a moment. Not 1 billion years after the beginning. Not 500 million. Under 300 million. The universe, at that point, was still in its severe youth, closer to cosmic dawn than to anything we would instinctively call maturity. And yet this galaxy is there. Not only there, but bright enough to force a revision of expectation. Before Webb, many models of the early universe did not prepare people for quite how many luminous galaxies might show up so soon, or how substantial some of them might already be. The old intuition was not absurd. Time matters in cosmic history. Structures need to form. Gas must collapse. Stars must ignite. Heavy elements must be forged inside those stars and thrown back out into space. All of that sounds like it should require breathing room. But the early universe is starting to look less like a place of scattered embers and more like a place where some furnaces were already burning hard. That is where the story stops being a simple record race and becomes more intimate. JADES-GS-Z14-0 is not impressive only because it is far away. It matters because its brightness implies activity, real structure, real star formation, enough built up, early enough, to make older assumptions feel smaller than the universe itself. This is the shift Webb keeps forcing on us. It is not merely finding earlier objects, it is finding earlier complexity. And then comes the part that makes the title feel exact. Webb did not only detect this galaxy with its near-infrared tools, it also caught it with MIRI at 7.7 microns. That detail can sound technical if you let it float by. It should not float by. It is one of the most revealing details in the entire story, because it means some of the physical information we most want from that galaxy has been stretched beyond the reach of where earlier deep observations could comfortably follow. Light that began in forms closer to visible optical signatures has been pulled outward into the mid-infrared. In other words, the universe did not merely send us a dim postcard from its youth. It sent one whose ink had been stretched across expanding space until we needed a colder instrument, tuned to longer wavelengths, just to read the writing. And once you can read that writing, you're no longer just looking at a distant smudge. You're beginning to ask what was happening inside it. Inside any galaxy, light carries more than brightness. It carries clues about gas, temperature, motion, chemical content, and the violence or calm of the recent star formation. Certain wavelengths matter because atoms and ions leave their signatures there. Hydrogen does. Oxygen does. These are not decorative details. They are the difference between seeing that something exists and beginning to understand what it is. That is why the MIRI detection matters so much. We are talking about a galaxy so distant, and therefore so early, that some of its key rest frame optical features have been shifted out beyond the territory where older instruments could follow them. The fingerprints did not disappear. They migrated, and Webb followed. You can think of it like a document scanned through the wrong machine. The words are still on the page, but the format has changed. To the scanner that used to work, the text is gone. To the right scanner, it returns. That is part of what has happened here. Human beings have not simply aimed a telescope farther into darkness. We have built the next scanner. For a long time, a lot of astronomy at the edge of the observable universe involved inference layered over uncertainty. A faint object might be a very distant galaxy. It might also be something closer, with dust or unusual color properties fooling the search. A candidate could look thrilling in a deep image and then shrink under scrutiny. That is not failure. That is how frontier science behaves when your tools are near their limits. But it also means there is a psychological difference between suspecting and knowing. Webb keeps turning suspecting into knowing. Its near-infrared camera can identify extraordinary candidates at the edge of cosmic dawn. Its spectrograph can then confirm redshifts, taking what looks like a plausible early galaxy and pinning down how far back we are truly seeing. And then MIRI opens another layer, because once those rest frame optical features slide far enough into the infrared, it becomes possible to ask more physical questions about what kind of galaxy this really was. Not only when it existed, but how intensely it was forming stars, how enriched its gas may already have been, how quickly the universe was manufacturing complexity. That is a very different kind of victory. There is something almost disorienting about this if you slow down enough to feel it. The light-reaching web from one of these galaxies may have left when the universe was younger than many people imagine a galaxy could meaningfully be. It travelled for more than 13 billion years. It crossed an expanding cosmos that kept stretching it farther from its original form, and yet when it finally arrives, it still carries evidence of physical processes in that ancient system. A signal that old is not mute, it whispers detail. The surprise is what those details suggest. In the older, simpler picture, the early universe had a certain expected emotional texture. You imagine darkness giving way gradually to the first stars, then the first small assemblies, then larger and brighter systems later on. That broad outline is still right. Webb has not overturned the fact that structure forms over time, but within that outline, the pace now looks more aggressive in some places than many people expected. The earliest substantial galaxies do not all look like hesitant beginnings. Some look busy, some look bright, some look as though the machinery of star formation was already running with unnerving confidence. And once that possibility opens, it keeps widening. Brightness in a galaxy this early is not a cosmetic feature. It points toward a great deal of energy being released by young stars. It suggests that gas was collapsing, cooling, fragmenting, igniting, and building structure fast enough to produce something visible across a staggering distance and time gulf. It suggests that the young universe, in at least some regions, was not waiting around politely for our theories to catch up. The campfires are turning into cities of a light far earlier than many people would have guessed. That metaphor matters, because it restores scale without drowning us in numbers. Imagine expecting a nearly dark landscape with a few isolated flames, and instead finding an illuminated settlement already glowing in the distance. Not a finished metropolis, not a mature modern skyline, but enough light to force a question. How did this place build up so quickly? That question becomes even sharper when we consider chemical enrichment. In the beginning, the universe had almost none of the heavier elements that later become planets: rocky crust, oceans, bodies, and blood. Those elements had to be made inside stars. Stars had to live, burn, and in many cases die before the cosmos could become chemically richer. So when Webb begins finding evidence that some early galaxies are already showing signs of substantial activity involving elements like oxygen, it means the first rounds of star formation and stellar processing may have happened with startling speed. The universe was learning complexity early. There is a tendency, especially in popular descriptions of the early cosmos, to picture it as pure and simple, a cleaner place, a more primitive place. That is true in one sense. But primitive can be misleading if it makes us imagine emptiness or passivity. Primitive can also mean unstable, compressed, eager to change. The early universe had denser conditions, fresh reservoirs of hydrogen and helium, and the relentless pull of gravity working on slight unevenness left over from the beginning. Under those conditions, change did not require elegance, it required opportunity. And opportunity was everywhere. So the more Webb looks, the more it confronts us with a universe that may have begun assembling luminous systems faster than expected. Not infinitely faster, not magically. There is no need to say anything careless or theatrical. The stronger truth is calmer than that. Webb is showing that some early galaxies became significant sooner than many pre-Webb forecasts would have comfortably predicted. And that difference matters because it changes how we think about the opening chapters of cosmic structure. It also changes what we mean by visibility. Before a telescope like this, some of these galaxies were not merely unseen in practice, they were partially inaccessible in principle, because the wavelengths carrying their useful information had moved beyond what the previous generation of observatories could truly exploit. That point is easy to understate. We often speak as if technology simply pushes one continuous frontier outward. In reality, a frontier can bend. Information can move from one observational domain into another. A question you ask with one instrument eventually becomes a question you can only pursue with a different one. That is what beyond previous limits really feels like here. Not a slogan, a transfer of reality from one sensory regime to the next. You can even feel that shift if you return, briefly, to your own body. Human eyes are narrow-band instruments. We live inside a tiny visible slice of the electromagnetic spectrum and treat it as normal because it is the slice our nervous systems inherited. We do not naturally see infrared. We do not wake up perceiving the heat glow of a wall or the subtle thermal outline of objects in a dark room, but those signals exist whether or not our senses include them. They are part of the world all the same. Cosmology has reached a version of that truth. The early universe was there in front of us, but not in a form our older tools could fully read. Webb does not create those galaxies. It does not invent the information. It extends our nervous system into a region of reality where ancient light has gone. And once you accept that, another surprise becomes easier to understand. Some of the earliest galaxies are not just visible. They seem able to affect the medium around them in ways that feel premature, almost rude, as if they began changing their environment before the broader universe was ready. The clearest case of that comes from a different object, one that takes this story from brightness and chemistry into something stranger. A galaxy whose light appears to be punching through a fog that should still have been thick around it. To understand why that is strange, we have to linger for a moment in one of the least intuitive periods of cosmic history. After the Big Bang, the universe was initially far too hot for atoms to hold together. Matter existed in a charged, ionized state. Then, as expansion cooled everything, electrons and protons combined into neutral hydrogen. That was a decisive change. Light could finally travel freely in a way it had not before, and the universe became transparent enough to release the ancient glow we now call the cosmic microwave background. But transparency did not mean clarity forever. Once neutral hydrogen filled space, it also became very good at blocking certain kinds of ultraviolet radiation. So the early universe developed a fog of a very particular kind. It was not fog in the ordinary sense, not droplets hanging in air, but the analogy is still useful because it captures the experience. Imagine a landscape where lamps begin turning on in the distance, but a thick, light-swallowing mist lies between you and them. Some wavelengths can make progress. Others are scattered or absorbed. The lamp exists. The light exists. The medium in between decides what reaches you. One of the most important signals in all of early universe astronomy is Lyman alpha, a spectral line associated with hydrogen. In the right context, detecting it from a very distant galaxy can tell us something about that galaxy and about the surrounding state of the universe. But there is a problem. During the era called reionization, much of intergalactic space should still have contained enough neutral hydrogen to choke off that line before it could travel far. In plain terms, the fog should have been thick, which makes the galaxy known as JADES-GS-Z13-1 so arresting. This object, observed at a redshift of about 13, appears to show unexpectedly strong Lyman alpha emission. That is not impossible. It is not a violation of physics, but it is surprising in exactly the right scientific way. The surprise is not sensational, it is structural. If the larger universe at that time still contained a great deal of neutral hydrogen, then how is this signal getting out so clearly? The leading possibilities tell us a lot about how science advances when the universe refuses to stay comfortably within prediction. Perhaps this galaxy sits inside an unusually large ionized bubble, a local region where intense radiation from young stars has already stripped electrons from surrounding hydrogen, making the fog temporarily thinner around it. Perhaps the stars inside it are unusually effective at producing hard radiation. Perhaps the geometry of the gas, inside and outside the galaxy, is more favorable than average for escape. Perhaps several of these things are true at once. Each explanation is plausible, none should be treated as final. And that uncertainty is part of the reward, not a weakness in the story. It tells us that Webb is now operating in a regime where the universe is giving us evidence faster than we can fully digest it. We are no longer waiting for the first faint hints. We are in contact with the beginning of complexity, and the beginning is answering back in a tone that is not entirely what we rehearsed for. There is a pattern emerging here. The first surprise is that substantial galaxies existed this early, and that some were brighter than many expected. The second is that their internal conditions may already include meaningful chemical enrichment and intense star formation. The third is that at least some of them appear capable of carving out, or inhabiting, clearer neighborhoods inside a still murky young cosmos. Each result modifies the emotional texture of the early universe. What looked, from a distance, like a nearly featureless dawn begins to resemble something more dynamic and uneven. Light does not arrive everywhere at once. Structure does not mature everywhere at the same pace. Some places race ahead. That matters because reionization is often described too smoothly. In simplified tellings, The universe passes from darkness to the first stars, and from there into a broad era when those stars and galaxies gradually ionize the neutral hydrogen around them, until intergalactic space becomes mostly transparent again. That overall story is sound. But what Webb is revealing is the local messiness inside the grand simplicity. Reionization may have been patchy, lopsided, intensely regional. Not a single curtain lifting at once, but a complicated weather system of clearing pockets and stubborn haze. You can almost see it if you allow yourself one physical image. Imagine flying over a continent at night after a storm. Some districts are still buried under cloud, others have broken open, and city lights blaze through sudden windows of clarity. From a distance, the map looks mottled, uncertain, alive. That may be closer in feeling to the young universe than the old, smoother mental picture many people carried around. And here again the title pays off in a deeper way. Webb is not only extending observational limits in distance, it is extending them into the physical state of the universe itself. Infrared light, recorded at wavelengths beyond earlier practical reach, is letting us ask not just what is out there, but what the surrounding cosmos was like when that light began its journey. The telescope is becoming a reader of conditions, not just a finder of objects. This is where the story becomes subtly unsettling in the best sense, because every time Webb succeeds, it exposes not only a distant galaxy, but a blind spot in our former intuition. We tend to think ignorance feels empty. It rarely does. It often feels normal. The pre-Webb picture of the earliest galaxies was not nonsense. It was a working map drawn at the edge of available evidence. But once the new evidence arrives, you realize how much of the old calm came from lack of access. Reality had not been simple, our view had been narrow. That lesson repeats across science. We describe a system one way, then a new instrument opens a previously inaccessible band of information, and the world becomes more textured than our confidence deserved. Ocean floors, bacterial life, the deep atmosphere of planets, the structure of the brain, the chemistry of exoplanets, the edges of the observable universe, again and again. The hidden world is not absent. It is waiting beyond the range we have not yet learned to read. Webb belongs to that lineage, and it sharpens an older philosophical mistake many of us make without noticing. We assume that what we fail to detect is probably not there, or not there in a meaningful way. But detection is always a negotiation between reality and instrument. Some truths are obvious at human scale because our senses evolved in the right environment for them. Others remain silent until the right tool arrives. The early universe did not become chemically active, structurally ambitious, or locally transformative the moment Webb launched. It had been that way all along. What changed was our side of the conversation. The emotional force of this is easy to miss if we only speak in headlines. Most distant galaxy confirmed, earliest light ever studied, unexpected signal from cosmic dawn. These are accurate enough as compressed summaries, but they flatten the deeper experience. The real experience is that human beings, with a species history too short to even register against cosmic time, have managed to build an instrument capable of detecting transformed light from a universe still emerging from its first major transitions. We are not merely extending a record book. We are participating in the slow repair of perception. And still, the frontier keeps moving. JADES-GS-Z14-0 is not the last word. The field did not stop at one astonishing object and declare the case closed. Another galaxy, MOM-Z14, has pushed the confirmed frontier slightly farther still, to a redshift of about 14.44. That means we're seeing it from roughly 280 million years after the Big Bang. The exact decimal places matter to specialists. The feeling matters to everyone. We are now operating in a region of time so early that the margin between one record and the next is measured against the opening instance of galaxy history. More importantly, this tells us something the record language alone can hide. The frontier is not being pushed by a single freak discovery. Webb keeps finding that the edge is occupied, not crowded in any ordinary sense, but populated enough to tell us the first substantial galaxies are not mythical one-offs glimpsed by luck. The early universe is beginning to look inhabited by more luminous, more detectable systems than many models once made comfortable. That brings us back to the question underneath all of this. If the universe could build galaxies this early, and some of them this bright, and some of them chemically this active, and some of them apparently capable of ionizing their surroundings enough to let difficult signals escape. Then what does that say about how quickly cosmic structure got underway? And what exactly were those first few 100 million years really like when the darkness started giving way? I'm staying inside the same continuous movement and pushing from surprising detections into what kind of early universe could produce them. This next stretch will deepen the causal picture without turning into a lecture. The safest answer is also the most interesting one. Those first few 100 million years were probably not calm in the way many people once imagined them. Not chaotic in a meaningless sense, not some lawless burst beyond explanation. The same gravity, the same atomic physics, the same broad cosmological framework still hold. But within that framework, the young universe may have found efficient ways to build luminous systems earlier than many models had prepared us for. Small differences in the timing of collapse, the supply of gas, the efficiency of star formation, the merger histories of tiny protogalactic structures, and the local radiation environment can compound rapidly when the universe is dense and young. In such a setting, a little earlier can become surprisingly visible very quickly. That matters because we often carry a misleading emotional assumption into cosmology. We imagine the early universe as a weaker version of the later one, as though everything must begin timidly and then only gradually become dramatic. But density changes that intuition. When the universe was much smaller, matter was packed more tightly. Gravity had less empty room to overcome. Regions that were only slightly denser than average could start pulling material inward. Once stars began to ignite, they did not merely light up their local neighborhoods, they changed them. Light is never only illumination. Radiation heats gas. It ionizes gas. Supernovae enrich gas. Stellar winds push on gas. Everything couples to everything else. So the opening era of galaxy formation was not a quiet assembly line. It was feedback from the beginning. Every successful burst of stars altered the next round of possibility. Some regions would have been slowed, stirred, disrupted. Others may have been compressed, enriched, or briefly made more favorable for further collapse. The first galaxies were not assembling in a passive background. They were helping write the conditions of the world around them. That is one reason Webb's recent detections feel so consequential. They are not just snapshots of isolated objects. They are clues to a process. The galaxies showing up at extreme redshift are evidence that by the time the universe was only a few 100 million years old, some places had already moved through several rounds of transformation. Gas had fallen together. Stars had formed. Radiation had escaped. Heavy elements had started to appear. In at least some cases, surrounding hydrogen may already have been altered enough to clear partial windows through the larger cosmic fog. The word early starts to lose its simplicity. Early for a human life means almost nothing has happened yet. Early in cosmic history can mean astonishing amounts have happened under the right conditions. That is one of the quiet, conceptual shocks Webb keeps delivering. We are being forced to separate youth from emptiness. The universe can be very young and already busy. You can feel this more strongly if you remember that time itself is not the only variable here. Scale matters, environment matters, initial conditions matter. If one patch of the young cosmos had a slight head start in density, and another had nearby structures that could merge or channel gas inward, their futures would diverge. One region might remain dim and tentative. Another might gather itself rapidly into something bright enough to be seen across almost the whole age of the universe. The early cosmos was not a uniform stage. It was a field of uneven opportunity. That is why the recent record holders are so important even beyond their individual novelty. Each one is a data point against the comforting idea that the first detectable galaxies were bound to be tiny, quiet, and mostly beyond meaningful physical interpretation. Instead, Webb keeps finding that some of these remote systems are substantial enough to teach us about the tempo of early cosmic assembly, not in the abstract, in detail. And detail changes the emotional force of discovery. There is a version of astronomy that can feel distant from human experience because it stays at the level of catalogue and classification. Redshift this, magnitude that, filter bands, line fluxes, confidence intervals, all necessary. But beneath that technical language is something much more immediate. We are trying to reconstruct what reality was doing before the sun existed. We are trying to infer weather from a fossil breeze, to recover the structure of a city from light that left before there were planets here to receive it. That is why one stretched spectral feature matters so much. It is a surviving trace of process. It tells us that something was not only present, but active. And activity is the thread that keeps pulling us forward. Once a galaxy like JADES-GS-Z 14-0 appears brighter than expected and yields signs consistent with strong star formation and enrichment, it becomes harder to preserve an older, gentler picture of the early universe. Once JADES-GS-Z 13-1 appears to let Lyman alpha out through conditions that should have made escape difficult, the surrounding environment stops looking smooth. Once MOM-Z14 reinforces that we are still pressing against a living frontier rather than a solitary anomaly, the field shifts from astonishment at a single object to re-evaluation of the era itself. This is how perception changes in science when the evidence is good enough. At first, one result feels exceptional. Then the second result suggests the first may not be alone. The third and fourth begin to pressure the background assumptions. Eventually, what once looked surprising becomes the new terrain on which theory has to stand. We are somewhere in that transition now. It is worth being careful here. Careful does not mean timid. It means precise. None of this requires reckless claims that cosmology has collapsed, or that everything we thought we knew was wrong. That kind of language usually reveals less understanding, not more. The large structure of the standard cosmological picture remains powerful. Expansion, dark matter, the growth of structure, the broad sequence from recombination to reionization to galaxy assembly, all of that still frames the discussion. The tension lies inside the details of pace, abundance, luminosity, and physical maturity. Webb is not tearing down the map. It is forcing us to redraw the finer roads. Sometimes that is even more profound. A total revolution can be emotionally satisfying, but reality often moves in more interesting ways. The universe keeps its deepest rules and still surprises us by what those rules permit when pushed into conditions we had not observed well before. That kind of surprise has more staying power. It does not depend on drama. It depends on scale meeting precision. And Webb is unusually good at that meeting point. Its success is not reducible to a single feature. The mirror matters, the wavelength coverage matters, the stability matters, the location matters, the cold matters, the interplay between instruments matters. A frontier object may first emerge in deep imaging, then be spectroscopically confirmed, then be probed for physical conditions at longer wavelengths. The achievement is cumulative. Webb is not one eye doing one trick. It is a coordinated system for following ancient light through multiple layers of meaning. That coordination is easy to overlook because the public face of astronomy is often an image. A beautiful image can carry a discovery to millions of people in a single day. But the scientific power behind the image lives in the less glamorous sequence that follows. Detect, verify, interpret. Ask which lines moved where. Ask what kind of stars could produce the emission. Ask what dust or gas conditions are implied. Ask whether a surprising signal can escape under expected conditions. Ask whether it hints at local clearing, unusual hardness of radiation, or something else not yet fully understood. In a strange way, the beauty comes later. Not because the pictures are not beautiful, but because the deeper beauty is in realizing that a telescope can catch light this altered and still pull physical meaning out of it. That is a harder beauty than color. It belongs to translation, to patience, to the fact that the universe can move a signal so far from its native form and yet leave enough coherence behind for us to recover something true. This is also where the human story re-enters, quietly but powerfully. Every one of these detections depends on an idea that would have sounded almost unreasonable for most of our species' existence. That minds evolved on one small world can build a machine delicate enough to detect radiation from galaxies that existed before that world formed. We take that for granted too easily. We hear about telescopes so often that the impossible becomes procedural. It is not procedural. A sun shield unfolds in space. Mirrors align. Instruments cool toward temperatures where their own glow will not drown the incoming whisper. Data arrives not as revelation but as pattern, noise, calibration, extraction, testing, caution, confirmation. Months of labor sit behind a line in a paper that can be read in seconds. And then, from all of that discipline, a strange fact appears. A galaxy from the first few 100 million years looks brighter than expected, more physically legible than expected, more active than expected. Reality does not shout, it accumulates pressure. And the pressure here is building toward a larger realization. When light is stretched enough, our ordinary categories begin to fail. Visible becomes infrared, early becomes active, distant becomes diagnostic. The old language of seeing farther is still true, but it is no longer enough. Webb is teaching us that the deepest frontier is not merely range, it is transformed information. It is learning to read a universe that does not deliver its oldest truths in their original colors. That is the scientific reality. The emotional one is just as strong. Because once you accept that light can leave a young galaxy as something closer to ordinary optical glow and arrive here billions of years later as mid-infrared radiation, only a deeply frozen instrument can catch. The night sky stops feeling straightforward forever. It becomes a delayed archive, and every successful observation is a reminder that absence and invisibility are not the same thing. That distinction matters far beyond astronomy. We live most of our lives inside a narrow band of reality and call it complete because it is familiar. We trust what arrives in the right form, at the right scale, through the right senses. Then an instrument extends us, and suddenly the world gains hidden structure. Infrared cameras reveal heat where the eye saw darkness. Microscopes reveal movement in what seemed still. Radio telescopes uncover violence in apparently quiet space. Webb belongs to that tradition, but it may be one of the most emotionally powerful examples because of the timescale involved. The hidden structure here is not merely small or faint, it is ancient beyond instinct. And because it is ancient, every misunderstanding we bring to it gets amplified. One of the most stubborn misunderstandings is the idea that looking deep into the universe is basically the same as looking at old photographs. That image helps at first. Light takes time to travel, so distant objects are seen as they were. Fair enough. But a photograph implies a fixed, faithful record. What Webb is dealing with is more like a letter that has crossed an ocean while the paper itself was slowly stretched. The message arrives late, but it also arrives changed. To read it, we have to understand not only the sender, but the transformation imposed by the journey. That is what redshift really becomes at the edge of the observable universe. Not a textbook term, a lived constraint on perception. A galaxy can begin by emitting ordinary ultraviolet and visible light from hot young stars and energized gas. By the time that radiation reaches us, it has been pulled into near-infrared or even mid-infrared wavelengths. The younger the universe was when the light was emitted, the more extreme that transformation can become. This means that if you want to study the earliest substantial galaxies with any physical richness, you cannot just keep doing more of the same observations. You need tools built for the shifted signal. This is why the line between Webb's instruments matters in a title like this. For many people, Webb is one machine, one eye, one giant leap in sensitivity. In practice, its power comes partly from the fact that its instruments occupy different parts of the infrared story. NIRCam is excellent for discovering distant candidates through deep imaging. NIRSpec can disperse the light and confirm their redshifts, turning distant-looking smudges into measured objects with real positions in cosmic time. MIRI reaches farther into the infrared, and that opens a crucial door once the rest-frame optical features we care about have slid beyond the range of the near-infrared instruments. That handoff is not a side note, it is the frontier becoming legible. With JADES-GS-Z 14-0, the 7.7 micron MIRI detection means we are no longer just holding on to the existence of an extraordinarily early galaxy. We are extending our reach into the domain where its shifted visible light fingerprints can still be caught. We are following the internal evidence farther down the redshift slope. The object is not merely there, it remains readable after more of its original light has crossed out of older practical reach. There is something almost intimate about that. Light left that galaxy in one form and arrived in another, but enough of its identity survived the transit that we can still infer what kind of activity powered it. If the MIRI flux includes strong contribution from lines associated with hydrogen and oxygen, then this was not an inert clump of matter waiting for history to begin. It was already alive with process, already making stars hard enough and fast enough to leave measurable signatures, already participating in the chemical story that, much later, makes rocky worlds and living bodies possible. That last point should be handled carefully, because it is easy to slide into sentiment here and lose the discipline that makes the story powerful. We do not need to pretend that these first galaxies were secretly about us. They were not. They existed billions of years before the Sun, before Earth, before oceans, before cells, before any eyes or languages or hands. But the chain is real all the same. The heavier elements that later become part of planets and people had to begin somewhere. They had to be forged in stars. So when Webb catches evidence that chemical enrichment was already underway this early, it is not just telling us about remote astrophysics. It is revealing how fast the universe began generating the conditions for later complexity. A young cosmos was already altering its own future. This is one reason the phrase cosmic dawn can be useful and misleading at once. Useful because it captures the sense of emergence. Misleading because dawn sounds gentle. It sounds gradual, almost pastel. But the actual process was harsher, more uneven, more kinetic. Gas collapsed into the first stars. Those stars emitted fierce radiation. Some exploded. Some polluted their surroundings with heavier elements. Some galaxies may have grown fast enough to ionize their local neighborhoods and punch partial holes in the larger neutral hydrogen fog. This was not a clean fade-in. It was a violent illumination scattered across a still dark world. And that scattered quality matters. When people imagine the universe becoming transparent again during reionization, they often picture a steady universal brightening, as though the fog simply thinned everywhere at the same pace. But the evidence emerging now suggests a more regional story. Pockets of clearing, islands of radiation, local victories over opacity while the wider intergalactic medium remained difficult. The early universe may have resembled a coastline in patchy weather, where one bay opens suddenly to sunlight while the next remains buried in cloud. That image helps explain why a signal like Lyman alpha can be so startling from a redshift around 13. It is not merely that the universe was young, it is that much of the space between that galaxy and us should still have been hostile to that line. So if the line escapes strongly enough to be seen, the galaxy is telling us something about its neighborhood, its internal engine, or both. Again, not a final answer, but a strong pressure on old expectations. And once enough pressure accumulates, language itself starts to lag behind. Early galaxies begins to sound too tidy. First galaxies starts to blur systems that may already have had non-trivial histories by the time we observe them. Even primitive becomes suspect if it encourages the idea of simplicity rather than intensity. There is a danger in words that feel familiar. They let us preserve an emotional picture long after the evidence has begun replacing it. What Webb is doing, at its best, is forcing emotional correction. Not just intellectual correction, emotional correction. It is one thing to know in the abstract that the universe was dynamic early on. It is another to feel, through a sequence of observations, that by 280 or 300 million years after the Big Bang some galaxies were already bright enough, active enough, and in certain cases physically interpretable enough to make our earlier mental picture feel underdeveloped. The difference between those two states is the difference between information and altered perception. That is why these results travel so well beyond specialist astronomy. They speak to a broader truth about how human beings encounter reality. Again and again, what seems absent turns out to be transformed. What seems simple turns out to be unresolved because our access was too narrow. What seems settled turns out to have been a resting place created by instrument limits. The world is not obliged to fit the emotional pace of our understanding. Still, there is something calming in the way science handles this when it's working well. Webb does not arrive and declare mythic truth. It accumulates evidence. A candidate appears in deep imaging. Follow-up refines the case. Spectroscopy secures the redshift. Additional wavelengths open deeper interpretation. One surprise appears, then another. Theories strain, adapt, improve. New observations are planned. Alternative explanations are tested. The process is patient enough to be trustworthy, even when the findings are startling. That patience is part of the beauty. A lesser culture of explanation might tell this story as triumph and shock alone. A more truthful one tells it as attention. Engineers, astronomers, analysts, modelers, instrument teams, observers, software pipelines, calibration work, repeated skepticism, repeated testing. quiet labour on a scale almost invisible to the public, all so that one line in one ancient spectrum can be interpreted with care. That is how reality becomes readable without being distorted by our hunger for spectacle. And the reward for that care is immense, because when the evidence is good, it does not just update a database, it changes the shape of the sky, it makes the darkness feel less blank and more layered. It reminds us that between what exists and what we can currently detect lies a moving boundary, and that some of the greatest discoveries in human history happen not when reality changes, but when that boundary does. Webb is standing on that boundary now, where ancient visible light has been stretched into deeper infrared than previous eras could fully exploit, and where some of the earliest galaxies are no longer merely hinted at. They are beginning to answer, in physical detail, the question of how soon the universe learned to become bright. And that question has a second edge to it, because brightness is not just about being easy to notice. Brightness is about energy moving through matter. It is about stars being born in sufficient numbers, and in some cases at sufficient mass, to flood their surroundings with radiation. It is about gas not merely existing, but being organized by gravity into places where fusion can begin. Once we phrase it that way, the early universe stops looking like a museum exhibit and starts looking like a working system. You can feel the shift most clearly if you compare the age of these galaxies to the age of things we call old in ordinary life. A human civilization can span a few thousand years. Recorded history is a blink. The age of the Earth is vast by comparison, but still local, still late. These Webb targets are coming from a time so early that even our Sun belongs to a much later chapter. And yet the galaxies we are seeing are not blank placeholders waiting for structure. They are already doing astrophysics in earnest. That should make us a little suspicious of our own instincts. We are very good at imagining long, slow processes when we want to sound serious. Mountains rise slowly, species evolve slowly, galaxies form slowly. There is truth in all of those statements, but also danger. Slowly can become a narcotic word. It can flatten variation and make us underestimate what intense conditions can accomplish in a relatively short interval. In the opening universe, a few 100 million years is not nothing. It is enough time for gravity, density, radiation, and repeated cycles of star formation to produce results that can surprise anyone who entered the story expecting only hesitation. This is why the new observations are not just records. A record can be emotionally shallow if all it offers is a more distant number. What Webb is giving us instead is a new texture of beginning. The first substantial galaxies are beginning to look less like isolated curiosities at the edge of possibility, and more like members of an early population whose properties we can start comparing, questioning, and interpreting. That move, from singular marvel to emerging class, is one of the quiet signs that a field is maturing fast. It also changes the way we think about what a telescope is for. In popular imagination, a telescope magnifies. That is the old child's idea. Bigger lens, closer view. Useful, but incomplete. Modern astronomy is often less about magnifying than decoding. A telescope collects photons, yes, but the real goal is to understand what those photons mean after distance. Dust, motion, gravity, temperature, and cosmic expansion have all left their marks. A good observatory is not simply an eye. It is part eye, part translator, part historian. Webb may be the clearest example of that in operation because it sits at a point where the translation is unavoidable. The youngest observable galaxies do not offer themselves to us in their native presentation. They arrive stretched. Their ultraviolet and visible emission has been pulled into infrared. Their internal lines have slid from one observational regime into another. Their faintness forces huge sensitivity. Their physical interpretation requires the interplay of multiple instruments and cautious inference. The telescope succeeds because it was designed around these facts rather than despite them. And once that design starts paying off, the implications spread outward. If early galaxies were already assembling stars and enriching gas faster than many models anticipated, then the timeline of some downstream processes may need refinement too. How quickly did the first generations of stars cycle matter back into their surroundings? How efficiently could small halos gather gas and keep it long enough to continue forming stars? How patchy was reionization in practice? How common were bright systems versus quieter ones? How much did local environment accelerate or suppress development? These are technical questions. But the human meaning under them is simple. How quickly did the universe become capable of complexity that could change itself? Webb is helping answer that by giving us access to galaxies old enough to count as among the earliest substantial builders, but visible enough to reveal internal action. The internal action matters because it rescues deep time from abstraction. Without it, all we have is distance and age, which are grand but emotionally thin if repeated too often. A galaxy 13.5 billion light-years away can become just another large number. But a galaxy that far away whose light now lands in the mid-infrared carrying traces of hydrogen and oxygen emission, that is different. That is a story. That is process surviving transit. That is the universe not only being ancient, but legible. There is a line hidden in all of this that deserves to be said cleanly. The earliest universe we can study is not merely a place we cannot visit. It is a place we cannot even see directly in the ordinary sense. We can only reconstruct it through transformed messengers. That is a profound condition to live under. Every claim about the dawn of galaxies has to move through that bottleneck. We do not stand there with our own eyes. We receive altered light in the present, and from it we infer the past. That sounds fragile, but the strength of physics is that the transformations are lawful. Wavelengths stretch in knowable ways. Atoms emit at characteristic energies. Spectra can be modelled, compared, tested. The message is changed, but not arbitrarily changed. That is why astronomy works. The universe distorts its old signals without erasing the code. And because the code survives, even partial readings can be revelatory. A MIRI detection at 7.7 microns is not just another point on a graph. It is evidence that we are now catching the shifted afterlife of light that once belonged to a younger, bluer, more visibly ordinary emission environment inside a very early galaxy. In its own time and place, some portion of that glow would have looked far more natural to human intuition than what arrives here. Only the long expansion between then and now makes it strange. In that sense, Webb is restoring something as much as discovering it. Not restoring the original photons exactly. Those have done what they did. But restoring the connection between present detection and ancient physical reality. It lets us take light that has crossed almost the full history of the cosmos, light stretched well beyond previous practical limits, and say with growing confidence, this is what was happening there. This gas was excited. These stars were forming. This galaxy was already making its mark. That phrase matters too. Making its mark. We are so used to seeing the early universe as prelude that we can forget the people inside future centuries are not the only ones allowed to matter. Those early galaxies were not rehearsals for later history. They were history. They were sites where matter was already moving from simplicity toward structure, from structure toward chemistry, from chemistry toward the long chain of possibility that eventually includes planets, atmospheres, geology, and life. Webb does not sentimentalize that chain, it makes it visible. There is also something instructive in the fact that these discoveries come through infrared at all. Visible light has a privileged place in human imagination because it is the band in which our world arrives to us each day. We trust it without effort. Infrared feels less immediate, more mediated, more technical, but that is an accident of biology. The universe has no obligation to reveal its deepest past in the wavelength range our retinas prefer. If the oldest accessible galaxies are now speaking most clearly in stretched infrared, then infrared is not secondary. It is primary for this question. It is where the hidden archive opens. And when an archive opens, familiar assumptions begin to loosen. The story stops being, we looked farther. It becomes, we entered the regime where the earliest visible truths of galaxies have crossed into another form, and we followed them there. That is a more precise story. It is also a more haunting one, because it suggests that reality is full of things that are not gone, not silent, not impossible to know, only shifted beyond the habits of old perception. Which is why Webb's recent discoveries do more than inform us about the first galaxies. They also expose something about the way knowledge grows. We do not advance simply by seeing more. We advance by learning what kind of seeing a transformed world requires. I've reached the point where the script turns from what Webb found into what those findings do to our model of cosmic dawn. I'm keeping the tempo calm and the continuity hidden, so the next stretch can widen the stakes without sounding like a new section. That lesson lands especially hard in astronomy, because the world being transformed is so far outside normal human timing. In ordinary life, when something changes form on its way to us, we notice it quickly. A voice warps through a bad speaker, a photograph fades in the sun, a letter arrives water-damaged. The distortion is local, familiar, manageable. Cosmic distortion is different. It unfolds across billions of years, across expanding space, across a history so long that not one human memory, not one civilization, not one species-level story can contain it. And still, the message survives enough for us to rebuild meaning from it. That should give us a deeper respect for the phrase recorded light. Webb did not go out and collect the early universe like a specimen in a jar. It received a signal that had been crossing a changing cosmos almost since the beginning of galaxies, and it recorded that signal with enough sensitivity and wavelength reach to preserve information older observatories could not properly hold on to. The phrase sounds simple. The act is not simple. It is an encounter between a present-day instrument and a deeply altered remnant of the past. And because that encounter is now happening at wavelengths beyond previous practical limits for this kind of work, it is pushing astronomy into a more physically mature phase of early galaxy study. We are no longer dealing only in silhouettes against the dark. We are beginning to pick up the shifted equivalents of internal diagnostics. That difference is enormous. A silhouette tells you that something stood there. A diagnostic line tells you something about how it lived. This is why the title's emotional center is not farther than ever in a generic sense. It is, the oldest visible truths are no longer arriving as visible light, and now we finally have the means to catch them anyway. Once you absorb that, the design of Webb itself starts to feel almost inevitable, as though the telescope is less a triumph of ambition than a carefully argued answer to a very old observational problem. Of course, the mirror had to be large. The photons are few. Of course, the observatory had to be cold. Infrared is merciless to warm hardware. Of course, the instrument suite had to span multiple infrared regimes. The earliest galaxy light would not politely remain in one observational window. It would keep moving as redshift piled up. The telescope had to be built for migration. That migration is the true frontier. It also explains why these discoveries carry more weight than the casual public language around them sometimes suggests. When people hear about the most distant known galaxy, many understandably imagine a ladder of records, each one a little farther, a little older, a little more extreme. That is not wrong, but it is incomplete to the point of hiding the real achievement. The deeper story is that each increment in redshift pushes more of a galaxy's original information out of familiar ranges and into more demanding ones. So advancing the frontier means advancing the translation itself. At lower redshifts, many questions can still be approached with tools that operate in more accessible bands. Push earlier, and the same physical features slide away. The universe becomes harder to interrogate, not because it ceases to contain answers, but because its answers have moved. There is something strangely beautiful in that. The cosmos does not deny us knowledge. It displaces it. And displacements create thresholds. JADES-GS-Z14-0 is one such threshold object because it sits in the regime where a galaxy less than 300 million years after the Big Bang is not only spectroscopically confirmed, but also detected by MIRI at 7.7 microns. That means the rest frame optical information has moved far enough that mid-infrared becomes part of the physical reading process. The object is therefore not just early, it is early in a way that forces observational handover. It makes the frontier visible. When a single galaxy does that, it is impressive. When additional galaxies at similar eras continue to appear, the implication deepens. The edge is no longer a lonely point. It starts to look like a zone. That is one reason MOM-Z14 matters beyond its place in the record book. The exact hierarchy of farthest confirmed galaxies will continue to evolve, as it should. Better data will refine candidates, confirm some, eliminate others, and push the line. But what matters emotionally and scientifically is that Webb is repeatedly operating in a part of cosmic history once treated as mostly inaccessible. It keeps showing that the opening few hundred million years contain systems luminous enough, and in some cases physically rich enough, to become subjects rather than rumors. Subjects rather than rumors. That may be the cleanest way to say what has changed. A rumor of a galaxy is a candidate in a deep field image, intriguing but fragile, A subject is something you can discuss in terms of star formation, ionized gas, chemical enrichment, and environmental effect. A rumor can excite the imagination. A subject can reshape theory. Webb is turning more of the early universe into subjects. There is also a subtle emotional correction inside that shift. We often talk as though the distant universe is mainly interesting because it is past. But these objects are not museum pieces, frozen in the flatness of chronology. They were dynamic systems in their own moment, and the more physically interpretable they become, the harder it is to treat them as generic stepping stones. Each one had structure, internal conditions, radiative power, surrounding gas, a local struggle with opacity, a place in the patchwork of reionization. In other words, they had context. Context is what turns deep time into reality. Without context, ancient galaxies remain symbols. With context, they become worlds of process, not worlds in the planetary sense, but environments where matter, light, and history were interacting in specific ways. That is what makes a spectral feature from 13.5 billion years ago feel almost unnervingly alive. The feature is not just evidence that light travelled, it is evidence that conditions existed. And once conditions enter the conversation, our idea of the young universe grows less serene. Take the old intuition that the earliest galaxies should be small, dim, chemically primitive, and difficult to distinguish from one another. There is still truth in parts of that, because many early systems surely were faint, small, and hard to study. Webb has not filled the early cosmos with giant mature spirals, but it has shown that the upper end of what was already possible by a few 100 million years after the Big Bang may be brighter and more evolved than many expected, enough so that some galaxies are visible, measurable, and conceptually disruptive. Disruptive in a disciplined way. The discipline matters because it keeps wonder from collapsing into nonsense. There is no need to tell this story as if every new detection means physics has failed. That would cheapen what is actually happening. The power of the moment is that a robust framework can still hold while its internal expectations get sharpened by reality. The broad cosmological picture survives. The details of early galaxy abundance, brightness, star formation efficiency, ionization environment, and chemical pace become more demanding. A good telescope does not destroy theory. It asks more from it. That is a healthier and more profound form of surprise. It leaves room for uncertainty without draining the scene of force. We do not yet know every reason why some galaxies appeared as bright as they did, or why certain signals seem to escape through a universe that should still have been relatively opaque. But the uncertainty is bounded by evidence, and the evidence has enough weight now to create a genuine shift in understanding. This is not speculative theatre. It is a real frontier under pressure. And frontiers under pressure have a particular feeling. They make old language sound worn. They make routine assumptions feel provisional. They create an odd blend of calm and unease, because the data are solid enough to trust while the implications are still settling into place. That is very close to where astronomy now stands with cosmic dawn. You can hear it in the way people discuss these observations. The excitement is obvious, but so is the care. Claims are tested against alternative explanations. Instrument systematics are checked. Spectroscopic confirmation is prized because it anchors the discussion. Physical interpretation is layered cautiously, because a single line can carry multiple possibilities. This restraint is not a drag on the story. It is what allows the story to become real. The universe is already strange enough. It does not need help from exaggeration. And the strangest part may be the simplest. These galaxies are not newly created by discovery. They have been shining, fading, evolving, and vanishing in the deep past for almost the entire age of the cosmos. What is new is that the transformed light reaching us now falls inside a human-built apparatus capable of reading farther into its stretched form than we could before. That is the hinge. Not creation, but access. Once access changes, the map changes. Once the map changes, memory changes. The sky you thought you knew becomes a delayed field of altered messages, and somewhere in that field are systems from the opening few 100 million years, already burning hard enough to tell us that the beginning was not empty, not patient, and not as quiet as we once imagined. Not as quiet and not as uniform. That is the next layer Webb keeps uncovering. We are used to speaking about the early universe as if it were a single condition. One clean atmospheric state stretched everywhere at once. But the farther we push into real observation, the more that phrase starts to split apart. There was no single early universe in the emotional sense. There were regions, gradients, pockets of rapid assembly and places that likely lagged behind. There were local clearings in a wider fog, neighborhoods where radiation changed the rules sooner, and probably vast volumes that remained much harder to light up. This matters because human beings have a strong instinct for averages. Averages calm us. They smooth the world into something manageable. But the cosmos is often built out of departures from the average. Galaxies form because matter was not perfectly even. Stars ignite because gas was not perfectly still. Early visibility arrives because some regions did not wait for the universe as a whole to become simple and transparent. They raced ahead. In that sense, Webb's detections are not just expanding a timeline. They are revealing a landscape. A landscape is a better way to think about cosmic dawn than a calendar page. A calendar tells you when. A landscape tells you where conditions differ, where the terrain rises, where one valley remains hidden while another catches light. The era of the first substantial galaxies may have looked less like a uniform sunrise, and more like isolated ridgelines brightening through cloud. One crest visible while the low ground still lies in shadow. That image helps explain both the brightness of some early galaxies and the difficulty of seeing certain signals from them. The universe did not become readable all at once. Readability spread unevenly. And that unevenness feeds directly into why infrared is so crucial. The photons reaching us from these galaxies are not only ancient, they are survivors of a hostile route. Some wavelengths were lost, scattered, or absorbed more easily by intervening gas. Others were stretched steadily by expansion until they landed in bands beyond what previous generations of observatories could fully exploit. So every successful observation is, in a sense, the visible edge of a selection process. We are learning not only what existed, but what kinds of messages could survive the trip and still be caught by the right instrument. That can sound abstract until you bring it back down to something almost bodily. Imagine being in a thick fog at night and trying to understand a distant place from what reaches you. A bright beam may make it through where a subtler glow fails. A low sound may carry where a higher one dies quickly in the air. If the weather shifts in one corridor, messages from one direction may suddenly arrive while others remain blocked. You would not just learn about the distant place. You would also learn about the medium between you and it. That is what these early universe observations are doing. They are telling us about galaxies, but they are also telling us about the state of space between those galaxies and us at the time the light began traveling. They teach us about the senders and the fog together. This is why reionization remains one of the most emotionally rich parts of the story. The universe after recombination was full of neutral hydrogen, and neutral hydrogen is not an innocent backdrop. It absorbs and reshapes what can move through it. Then the first luminous objects begin to appear, and their radiation starts changing that medium. Electrons are stripped away again. Bubbles of ionized gas expand. The fog thins locally before it thins globally. The whole era is a negotiation between matter and light. What Webb has done is push us closer to watching that negotiation from inside. Not directly, of course. We are still reconstructing it from transformed signals, but the reconstruction is getting intimate enough that the old broad brush version no longer feels sufficient. It is no longer enough to say that early stars and galaxies reionize the universe. We want to know how fast, how patchy, how locally intense, and under what kinds of galactic conditions. We want to know what the first strong sources looked like, how efficiently they formed stars, how much of their radiation escaped, and how quickly the chemistry of their gas became more complex. That appetite for detail is itself a sign that the field has changed. You do not ask those questions with confidence unless the observations have become strong enough to bear them. And Webb has made them bearable. There is a quiet boldness in that word, bearable. Some scientific questions remain too heavy for the evidence available. Ask them too early, and they collapse into speculation. Ask them after a leap in instrumentation, and the same questions suddenly become productive. That is exactly where we are with the dawn of galaxies. The topic has crossed from philosophical curiosity to physically constrained inquiry. We are still far from knowing everything, but we're no longer staring into a blur and pretending it is enough. One result of that shift is that the early universe is becoming less mythical and more particular. For a long time, the very first galaxies occupied the imagination almost like legendary beings. They were foundational, but remote, abstract, difficult to picture in any concrete way. Webb is changing that. The first substantial galaxies are beginning to acquire profiles. Some appear brighter than expected. Some show signs of rapid star formation. Some may already contain enough oxygen and other heavier elements to indicate surprisingly fast enrichment. Some appear to be situated in, or to have generated, conditions that let difficult spectral lines escape. Particularity is a profound kind of closeness. It does not make these objects less distant. It makes them less symbolic. They stop being stand-ins for the early universe and become examples of what the early universe could actually produce. Once that happens, the imagination has to mature too. You can no longer get away with treating cosmic dawn as a poetic haze populated by vague first lights. You have to contend with vigorous systems, uneven environments, and a pace of development that may outrun the emotional simplicity of older stories. The older stories were not useless. They got us here. Simplicity is often the first bridge into understanding, but every bridge has a point where it ends, and if you keep walking as though the simple version is still sufficient, you eventually step into empty space. Webb keeps bringing us to that edge and then extending the bridge just enough to show how much more complicated the ground beneath it really is. That is one of the reasons the telescope has become more than a machine in public consciousness. It functions almost like a correction to human scale itself. Our intuitions are tuned to local light, short delays, and modest distances. Webb operates where all of that breaks. It works with photons that began traveling before our world existed. Photons stretched beyond visible recognition. Photons so faint that the observatory must become almost unnaturally quiet to register them. In doing so, it trains us to think past our inherited limits. There is a humbling side to that, but not a humiliating one. It does not reduce us to irrelevance. Quite the opposite. The more alien the observational challenge becomes, the more extraordinary it is that minds like ours can meet it. A species that evolved to navigate daylight, shadows, faces, weather, and terrain has taught itself to read mid-infrared signals from the first few 100 million years of cosmic history. That fact should never become routine. Routine is the enemy of wonder. And modern science, perhaps because it succeeds so often, risks making its most impossible achievements feel procedural. A launch happens, a deployment happens, data comes down, papers appear, headlines circulate, another record is noted. But beneath that routine surface lies something almost absurdly delicate. A precisely aligned, deeply cooled observatory stationed in space, holding steady enough to detect ancient stretched light that previous eras of astronomy could not follow into the same physical depth. The absurdity is what makes it beautiful. It is not beautiful because it is flashy. It is beautiful because it is so exact. Because each part of the system exists to serve a reality that never had to become legible to us. Because the cold, the mirror, the wavelength range, the detectors, the software, the spectrographs, the calibration, the analysis, all of it is aimed at one profound task, making altered messages from the young universe readable without pretending they arrived unchanged. And once readability improves, so does judgment. Some theories gain support, others become strained, parameters shift, expectations become more careful. The pace of galaxy assembly in the first few 100 million years is no longer a matter to be discussed from a distance alone. It is becoming something we can test against objects whose light reaches into observational regimes beyond previous limits. The field is entering an era where the first substantial galaxies are not merely points of awe. They are pressures on explanation. That pressure is good. It keeps science alive. It also keeps the story alive, because every new confirmation does two things at once. It shows us one more ancient system, and it reminds us that our earlier picture was partly a shadow cast by the boundaries of older instruments. Webb is not only expanding the map, it is exposing the old edge where the map used to stop, and asking us to feel what lived beyond it all along. That feeling is worth staying with, because it changes the emotional center of discovery. We often imagine a new telescope as a spotlight aimed into darkness, but what Webb has really done is more subtle. It has shown that darkness itself was misleading. Some of what looked dark was simply displaced. Some of what seemed unreachable was already crossing the universe toward us, just outside the wavelength range where older observatories could fully turn it into understanding. In that sense, Webb did not only extend our view, it corrected our idea of what hidden means. Hidden does not always mean absent. Sometimes it means translated. That is the principle underneath everything in this story. The first galaxies did not conceal themselves on purpose. The expanding universe altered their light. The farther back we look, the more severe that alteration becomes. So the question is never just whether enough photons survive. It is whether we have built the right kind of receiver for the photons that do survive. Once you see it that way, the recent discoveries stop feeling like lucky breaks and start feeling like the natural result of finally matching the instrument to the problem. And the problem was always larger than distance. Distance sounds passive. It suggests that if something is far enough away, the main challenge is patience and power. But the early universe forces us to think in terms of transformation, filtering, and physical consequence. Light is stretched by expansion. Certain features move into new spectral territory. The medium around the earliest galaxies shapes what escapes. The intergalactic medium shapes what travels. The telescope's own temperature determines what can be separated from background glow. It is not one barrier, it is a chain of barriers, each one interacting with the next. That is why the detections feel so earned. By the time a galaxy like JADES-GS-Z14-0 becomes physically interpretable, an entire system of conditions has been satisfied. The galaxy had to form early enough, and brightly enough, to send a usable signal. The signal had to survive a long journey through a changing cosmos. It had to land in wavelengths Webb could capture. The observatory had to remain quiet enough not to drown it in its own heat. The data had to be cleaned, calibrated, confirmed, and tested. Only then does the public hear a line that sounds simple. One of the most distant galaxies ever confirmed has also been detected at 7.7 microns. But simplicity on the surface is often what disciplined complexity looks like once it works. And when it works, it changes the scale of what counts as ordinary. That may be the deepest effect of Webb so far. It keeps taking events and conditions that once would have sounded almost impossibly remote and making them part of normal scientific discussion. A galaxy under 300 million years after the Big Bang. Another at around 280 million years. Signs of active star formation. Evidence consistent with surprisingly rapid chemical enrichment. Unexpectedly strong escape of a line that should have struggled through surrounding neutral hydrogen. These are not fringe anecdotes anymore. They are part of the emerging baseline for how we talk about cosmic dawn. The baseline moved. That phrase carries more force than it first appears to. Scientific revolutions are often imagined as explosive reversals. But some of the most consequential changes happen when the baseline moves quietly. Yesterday's edge case becomes today's working assumption. Yesterday's possible but unlikely becomes today's model input. Yesterday's simplified narrative becomes today's introductory approximation before the real story begins. Webb is moving the baseline on early galaxy formation, and because of that, the opening universe is becoming less speculative in texture and more observationally inhabited. Inhabited is the right word, though not in the sentimental sense. The opening universe was inhabited by process, by collapsing gas, by hard radiation, by stellar birth and death, by chemistry beginning to thicken, by bubbles of ionization inside a wider neutral medium, by asymmetries that made one region race ahead while another remained obscure. It was not a blank waiting room for later grandeur. It was already full of consequence. That matters for another reason too. It rescues the phrase, first few 100 million years, from becoming an empty number. Large numbers in cosmology can numb us if they are repeated without consequence. Billions of light years, hundreds of millions of years, redshift 14.32, redshift 14.44, impressive, yes, but only if the number remains connected to something your mind can hold. The real connective tissue is this. By the time the universe was a few 100 million years old, some places had already built galaxies bright enough to see across almost the entire age of the cosmos, active enough to produce strong internal signatures, and in at least some cases capable of changing the transparency of their local surroundings. Now the number lives. This is also where the story becomes a little more intimate than most public summaries allow, because what Webb is doing is not only observing those galaxies, It is observing our own former limits. Every early object that turns out to be brighter, clearer, or more physically rich than expected marks the contour of an older blindness. Not a foolish blindness, an honest one, created by the fact that instruments define what a period of science can comfortably imagine. We usually theorize a little beyond what we can observe, but our imagination still tends to orbit the evidence we have. So when the evidence changes enough, imagination has to be retrained. That retraining is one of the quiet dramas of science. A field grows used to one picture of the early universe. Then a new observatory starts delivering observations that are not impossible under the old framework, but are awkward enough to demand reconsideration. Researchers debate interpretation, refine selection criteria, rethink star formation efficiencies, question assumptions about dust, luminosity functions, escape fractions, enrichment timescales. None of that is flashy in the public sense, yet inside it is the real pulse of discovery, reality making theory more specific. Webb is doing that at extraordinary speed. Part of the reason is that it operates at a threshold where multiple limitations are being relaxed at once. More collecting area, deeper infrared reach, better sensitivity, access to spectroscopy in a regime where confirmation matters desperately, and then, crucially, MIRI opening a farther band where some of the shifted optical information from these extreme redshift galaxies can still be caught. It is the combination that changes the game. Remove one piece, and the frontier narrows again. This is why it would be too simple to say that Webb just sees farther than Hubble. True, but insufficient. What matters is not merely that Webb looks deeper, it follows ancient light farther through its transformation. Hubble could reveal the existence of a deep universe with unmatched beauty and rigor. Webb is taking the next step into a regime where the first substantial galaxies can be investigated as systems, not only admired as faint relics. The handover between those eras is one of the great continuities in modern astronomy, and continuities matter as much as breakthroughs. They remind us that discovery is cumulative. Webb did not arrive in a vacuum. It rests on decades of physics, engineering, cryogenics, detector design, orbital planning, spectroscopy, image analysis, theoretical modeling, and the older telescopes that defined the questions in the first place. The public tends to meet the finished revelation. The deeper truth is that each revelation stands on thousands of quieter acts of attention. Maybe that is why these observations feel so calming even as they disturb old assumptions. There is no chaos in the method, no panic in the interpretation. The universe can become stranger and still become clearer at the same time. That is one of the most reassuring things science offers when it is done well. Surprise does not have to mean confusion. Surprise can mean reality finally arriving in a form we are prepared to understand. Prepared but not finished. Because every answer Webb provides opens the next pressure point. If galaxies this early can already appear this bright, what does that imply about the abundance of lower luminosity systems we cannot yet characterize as easily? If some show signs of rapid enrichment, how quickly did the first stellar generations live and die? If Lyman alpha escapes in unexpectedly strong ways from some regions, what does that say about local ionized bubbles, the hardness of stellar radiation fields, or the topology of reionization itself? If one object was once dismissed as too extreme to be likely, and then another appears nearby in conceptual space, how many more are waiting in the data? A frontier starts to feel real when it stops ending. That is where cosmic dawn is now, not solved, not reduced to a neat sequence, not frozen in a set of iconic discoveries. It is becoming denser with evidence, more structured with interpretation, more resistant to the old simple mental image of a thinly populated beginning. And all of this is happening because we now have an observatory capable of catching ancient light after the universe has stretched it beyond the previous practical limits of our perception. Once you truly feel that, a familiar sentence becomes newly strange. We live under the same sky our ancestors did. The stars still rise, darkness still gathers, but the archive above us is no longer the same archive to us, because we have learned to read farther into what the darkness has been hiding in altered form. And that changes what it means to look up. For most of human history, the night sky was a ceiling of immediate mysteries. It guided travel, marked seasons, anchored myth, suggested permanence. Even after astronomy became a precision science, there was still a strong emotional tendency to treat the sky as a display, points of light spread across distance, some closer, some farther, all part of a grand but relatively straightforward visual order. Webb has unsettled that order in a subtle way. It has shown that the sky is not just a display, it is a field of delayed, stretched, and filtered messages, and some of its deepest truths only appear when we follow those messages beyond the range in which they began. That means the night is not merely dark and it is encoded. Once a thought like that really settles in, even common words begin to feel different. Starlight sounds simpler than it is. Galaxy sounds more familiar than it deserves to. Seeing sounds almost innocent, but the farther we go, the less innocence remains. We are not standing under a transparent dome. We are standing inside an electromagnetic archive shaped by expansion, intervening matter, instrument limits, and the very recent fact that one species on one planet has begun to decode more of it than ever before. This is why a discovery at 7.7 microns can feel larger than the number itself. The number is only the visible edge of a deeper shift. It tells us that some of the information we most want from galaxies near the dawn of structure has moved into a spectral region that earlier eras could not exploit in the same way. It tells us that a machine cold enough, steady enough, and sensitive enough has now caught that migrated information and held it long enough for us to ask physical questions of it. The wavelength is real, the meaning is the point, and the meaning keeps widening. If a galaxy like JADES-GS-Z 14-0 already shows signs consistent with intense recent star formation and substantial internal activity less than 300 million years after the Big Bang, then the first durable chapter of cosmic structure is not beginning with a whisper. If a galaxy like JADES-GS-Z 13-1 appears able to let Lyman alpha escape despite an era when the broader universe should still have been difficult for that line, then the local geography of reionization matters more vividly than many people imagined. If MOM-Z14 and similar objects continue to populate the frontier, then the edge of the observable young universe is becoming not only visible, but inhabited by systems with enough character to challenge our sense of how beginnings behave. Beginnings behave more aggressively than we expected. That is one of the script's quiet central truths, and it is worth holding carefully, not aggressively in a cinematic, overblown sense. Aggressively in the sense that matter under early cosmic conditions appears capable of organizing itself into bright, physically consequential structures sooner than older intuition made emotionally comfortable. Gravity did not waste time. Gas did not remain passive. The first galaxies, at least in some places, may have moved from possibility to consequence at a pace that now demands a richer story. A richer story also requires a richer relationship with uncertainty. That may sound like a step away from certainty, but it is actually a step toward mature clarity. We know more now, and because we know more, the unknowns become sharper rather than blurrier. We can ask more precise questions. Why are some early galaxies brighter than expected? How representative are the currently detected luminous systems of the larger underlying population? How much dust or heavy element enrichment is already present in some of these objects? And how quickly could it have accumulated? What conditions allow hard-to-escape spectral features to get out? How patchy was reionization in local practice rather than in broad average? Those questions have texture now because the observations have texture. That is another thing Webb has changed. It has made cosmic dawn less like a concept and more like an environment. An environment has conditions. It has gradients, bottlenecks, asymmetries, thresholds. It has local surprises. It contains different kinds of places. The first substantial galaxies are not just dates on a line. They're actors inside an environment where light and matter were still negotiating the large-scale transparency of the universe. Some galaxies may have lived inside neighborhoods already carved into relative clarity. Others may remain effectively hidden because their signals cannot yet fight free of distance, redshift, and the intergalactic medium in the right way. So even the galaxies we do see may be teaching us partly through selection. The visible frontier is shaped by what survives and what our instruments can catch. That does not weaken the discoveries, it deepens them. Because it reminds us that observation is not a passive mirror of reality. It is an interaction between reality, root, and receiver. This is why there is something almost philosophical about Webb without the need for any vague cosmic sentiment. The telescope is teaching a disciplined lesson about perception. There are truths that remain fully real while being inaccessible to the senses and technologies we currently possess. They do not become true when we detect them. They become detectable when we finally build the right bridge. That lesson is easy to say and harder to feel. We spend most of our lives in a world where the visible seems sufficient. A chair is where we see it. A road is where it appears. Heat, radio waves, ultraviolet, X-rays, infrared, the chemistry inside a star, the magnetic architecture around a black hole, the dawn light of galaxies shifted out of visible range. Those belong to specialists, instruments, diagrams. But once you start following what Webb is actually doing, that division weakens. You begin to feel that the visible world is only the comfortable subset. The real world is much broader, and some of its oldest surviving records live beyond the narrow slice our bodies evolved to trust. Webb is not just gathering data, it is tutoring intuition. That tutoring takes patience, because our inherited intuitions are strong. We still want the first galaxies to behave like simple beginnings. We still want looking far away to feel like peering through a bigger window. We still want the dark sky to feel blank between the bright points. Yet each new Webb result presses gently against those desires. The first substantial galaxies are not only there, they are active. The light is not only old, it is altered. The darkness is not only empty, it is filled with delayed structure whose accessibility depends on wavelength, survival, and instrumentation. And the more that picture settles in, the more extraordinary the observatory itself becomes. A machine with a segmented mirror and a tennis court-sized shield waits in deep space. It turns its instruments toward tiny regions of sky that, to an unaided human eye, would reveal nothing of the sort. It holds itself still enough, cold enough, and quiet enough to register photons that began traveling before the Earth existed. It sends those measurements home. Human beings reduce noise, verify calibration, test interpretations, compare models, doubt themselves, recheck assumptions, and eventually say something with care that would once have sounded almost impossible. We have detected and begun physically interpreting infrared light from galaxies in the first few 100 million years after the Big Bang, at wavelengths beyond previous practical limits for such work. That sentence should feel impossible. It should retain some friction every time we hear it. Otherwise we lose the human proportion of the achievement, and human proportion matters here, because the discoveries are so large that they can flatten the people involved if we're not careful. A galaxy at redshift 14 can make human history feel microscopic, but the act of detecting it is a human act. The choice to build a colder observatory rather than a merely larger one is a human insight. The recognition that transformed light requires a transformed instrument is a human recognition. The discipline not to exaggerate beyond evidence is a human discipline. The whole story is about scale beyond us and mind within us at the same time. That balance is rare. It is one reason cosmology can feel so cleansing when it is told honestly. It does not flatter us as central, but it does not erase us either. We are small in the face of deep time. We are also the beings who can learn to read deep time. Those two truths belong together. And the more Webb keeps working, the stronger that union becomes. Because the telescope is not nearing the end of a neat checklist. It is opening a domain. More candidates will come. Some will be confirmed. Some will fail. New spectra will sharpen the frontier. Better analyses will revise earlier interpretations. The record line will move again. But the larger shift has already happened. We now know that the young universe is physically more readable, at more extreme redshift, and through more deeply stretched infrared light than the previous era of astronomy allowed. That knowledge leaves a residue. It lingers the next time you imagine the first galaxies. They no longer appear as tiny abstract sparks floating in a smooth, nearly empty cosmos. They appear as working systems in a patchy environment, already producing radiation, chemistry, and consequence. They appear as senders of altered messages, and the sky above us, once treated as a simple visual field, begins to feel more like a vast correspondence whose oldest letters only now have the right reader. The right reader, and just in time for us to understand what kind of correspondence this has always been. Because once you think of the universe as sending messages, another misconception falls away. We tend to imagine that the message is the image. A beautiful deep field photograph appears, and we feel that the universe has revealed itself. In one sense, it has. Images matter. They rearrange public imagination in a single glance. But the most important message is often not the picture itself. It is the physics hidden inside the light that made the picture possible. It is the spectrum, the shift, the line that moved farther than expected, the wavelength at which a source can still be detected, the clue that turns a distant point into a story about gas, stars, enrichment, and environmental change. That is why Webb's recent frontier work feels so different from older versions of deepest image ever excitement. The images are still beautiful, but beauty is no longer carrying the whole burden. The deeper burden is interpretation. The telescope is not just showing us that early galaxies existed, it is helping tell us what they were already doing, and that is a far more intimate kind of contact. It also forces us to take time seriously in a new way. We often speak about the age of the universe as if it were one smooth quantity, almost a background number, around 13.8 billion years, familiar enough by now that many people can say it without feeling much. But the first few 100 million years are not merely a small fraction of that total. They are a radically different regime, where the first durable structures are appearing, where the intergalactic medium is still in transition, where the first generations of stars and galaxies are beginning to alter the chemistry and transparency of the cosmos itself. It is one of the great thresholds in reality, and Webb is now close enough to that threshold that we're no longer only outlining its existence. We're starting to watch its consequences accumulate. A threshold always has two meanings. It marks what has been crossed, and it marks what still lies beyond. That second meaning is part of the fascination here. For all Webb has already done, the first few 100 million years are not suddenly transparent in every sense. Far from it. We're still seeing selected objects, often the brighter ones, the more favourable ones, the ones whose signals survive and fall into detectable bands. The full population of faint early galaxies remains more elusive. Some of the younger structures may still lie below current interpretive reach. There are still uncertainties about how representative the currently known record holders are of the broader young universe. The archive is open farther than before, but it is not exhausted. And that incompleteness is not frustrating in the empty way people sometimes imagine. It is generative. It tells us we're in the early phase of real contact. There is a particular excitement that belongs only to that phase, not the excitement of pure speculation, when almost anything can be imagined because almost nothing is anchored, not the excitement of closure, when the major story is already known and the remaining work is detail, but the middle state, where the evidence has become strong enough to demand revisions while still leaving room for genuine surprise. That is where cosmic dawn now sits, strong enough to reshape understanding, open enough to keep deepening. Webb has made that middle state possible by altering a simple fact of access. It reaches where the transformed light now is. That may be the most important sentence in the entire piece, because it is so easy to miss. The early universe did not become visible because we insisted hard enough. It became more readable because we built the observational equivalent of a listener tuned to the changed pitch. That is what infrared means here. Not just heat, not just a technical band on a detector specification sheet, but the location where ancient visible truths now live after expansion has stretched them out of their original form. A visible lighthouse beam becoming something closer to invisible glow by the time it reaches shore. A voice falling so low that the old microphone no longer registers it. A page whose writing has slid off one scanner and onto another. These analogies are imperfect, but they all point toward the same reality. We did not simply look harder, we followed the migration. And migration has consequences for meaning. Once the first galaxies migrate out of the easy language of visible light and into deep infrared, our relationship to them changes. We are no longer receiving them in a sensory register that feels intuitive. Every insight has to be translated back into human-scale understanding. This line means ionized gas. That flux may indicate vigorous star formation. This wavelength implies the original feature has been stretched by an enormous factor. This detection suggests a galaxy substantial enough to surprise pre-Webb expectations. The work becomes interpretive from the beginning. In a strange way, that makes the experience more human, not less. We sometimes imagine that direct vision is the purest kind of contact and translation is a compromise. But almost all serious knowledge is translated. We translate numbers into images, spectra into physics, fossils into ecosystems, seismic waves into planetary interiors, genomes into histories of life. Webb is simply making that condition impossible to ignore. The early universe cannot be approached as a raw visual fact. It can only be approached as transformed evidence patiently made meaningful. That patience deserves more attention than it usually gets, because behind every most distant confirmed galaxy headline is a culture of restraint that keeps the discovery from becoming noise. Distant-looking sources can be deceptive. Photometric estimates can shift. Spectroscopic confirmation matters because it narrows ambiguity and puts the object on firmer ground. Interpretation of emission features requires care because multiple processes can contribute. Even a strong surprise, like unexpectedly visible Lyman alpha at very high redshift, becomes scientifically valuable only when it is handled without haste. Webb's greatness lies not only in what it reveals, but in how well it supports that kind of careful revelation. That is why the story remains calming rather than frantic. The universe is getting stranger, but it is getting stranger through evidence, not through panic. There is dignity in that. A mature frontier does not need hype. It needs accuracy and enough imaginative discipline to let the facts carry their own force. The facts here are already more than enough. Galaxies less than 300 million years after the Big Bang are not only being located but physically probed. Light associated with their internal conditions has been followed into deeper infrared regimes than earlier eras could usefully exploit for this work. The early universe is proving more structured, more active, and more unevenly transformed than many people once felt. Those truths do not need decoration. They need room. Room to expand inside the mind the way the universe itself expanded around the light. Room for an old intuitive picture to loosen. Room for a more exact image to take its place. Not a simpler one, but a more honest one. A young universe full of a local intensity. A fog that clears patch by patch. A population of early galaxies beginning to emerge not as vague first lights, but as systems with internal life. An observatory so cold that it can catch the stretched remnants of their original glow. A species patient enough to learn from that. There is something deeply reassuring in the fact that reality rewards patience like this. So much of ordinary life punishes slowness. Speed dominates, immediate reaction dominates. The deep universe works by another rhythm. To understand it, we cool a telescope, wait for ancient photons, reduce the noise, measure carefully, and let the consequences unfold over time. There is almost a moral quality to that, though it does not need to be moralized. Attention matters, quiet matters. Reality yields to them. And what it is yielding, in this case, is a sharper picture of how soon complexity began to matter. That phrase is worth pausing over. Complexity began to matter very early. Not life, not planets, not anything familiar in the biological sense, but cosmic complexity in the structural and chemical sense. Matter clumped, stars formed, radiation escaped, heavy elements began to appear. Some galaxies lit themselves and their local surroundings strongly enough that, across nearly the whole age of the universe, we can still catch the transformed evidence. The beginning was not an empty waiting period. It was already becoming consequential. Once you accept that, the early universe stops feeling like prehistory in the dull sense. It becomes the moment when consequence first starts taking hold, and Webb, by recording infrared light beyond previous limits, is allowing us to witness that moment not as myth, not as vague grandeur, but as a readable physical reality whose first durable messages are only now arriving in a form we can finally answer. Answer is the right word, because astronomy at this depth begins to feel less like passive observation and more like delayed conversation. Not a conversation in any mystical sense. The universe does not speak to us with intention, but there is still an exchange of a kind. Conditions in the young cosmos produced light with certain properties. Expansion altered that light. Matter along the way filtered some parts of it and allowed others through. A telescope built billions of years later received what survived. Human beings interpreted the signal and reconstructed something true about the source. Question, answer. Not in real time. Not in one language, but in a chain of lawful transformation that still lets meaning cross unimaginable distances. That chain is one of the great miracles of science, and it can be described without any cheap mysticism at all. Atoms behave consistently. Radiation carries structure. Physical laws hold over deep time. Those are dry statements on paper. In practice, they mean that a galaxy which existed before the Earth formed can still leave behind readable evidence in the present. The cosmos is not only immense, it is coherent enough for memory. Webb is exploiting that coherence at a depth previous eras could not manage. And because it can, something subtle happens to our sense of the past. The earliest substantial galaxies stop feeling merely ancient and start feeling adjacent in a more technical, but also more intimate way. Not adjacent in distance, obviously, but adjacent in legibility. Their signals enter our instruments, their conditions become inferable, their strangeness becomes specific. The gap between too far to imagine clearly and far enough to study physically is one of the most important gaps a civilization can close. That is what these recent observations are helping close. You can hear the shift in the kinds of statements now becoming possible. Not just that an object lies at extraordinary redshift, but that it may already be chemically enriched. Not just that a source is present, but that its flux at a longer wavelength is consistent with strong internal emission features. Not just that a galaxy existed in a foggy era, but that a signal which should have struggled to escape appears unexpectedly visible. The universe at cosmic dawn is becoming less like a distant silhouette and more like a place where conditions can be argued about with evidence. Evidence changes the emotional temperature of wonder. Wonder without evidence can be beautiful, but it is unstable. It floats too easily into projection. Evidence gives wonder edges. It makes the experience less dreamy and more durable. That is exactly the kind of wonder Webb produces, the kind that comes from a measured line in a spectrum, a detection at a wavelength that should matter, a pattern in the data that keeps surviving skeptical checks. The universe becomes stranger, but also harder to dismiss as a story we are merely telling ourselves. And one of the strangest things it is now telling us is that the opening era of galaxies may have matured, in some regions, with startling speed. Again, speed should be handled carefully. A few 100 million years is not a trivial interval, but relative to the age of the universe, and relative to older intuition about how quickly substantial, bright, physically rich galaxies should emerge, it is early enough to feel almost abrupt. The point is not that galaxies sprang into full maturity overnight. The point is that by the time the cosmos was still in what we would reasonably call its opening act, some systems were already forceful enough to be visible across nearly all of cosmic time, and complex enough to pressure our theories. This is where a lot of people's mental picture still lags behind the evidence. We are comfortable imagining the early universe as a stage of simplicity, because simplicity sounds cleaner and more intuitive than rapid layered development. But rapid layered development is what many physical systems do under the right conditions. In a dense, evolving medium with gravity constantly amplifying slight imbalances, the path from small irregularities to meaningful structure is not leisurely in every region. Some regions can run. That word fits the data better than many gentler alternatives. Some regions ran. They raced ahead in luminosity, star formation, and perhaps in their ability to carve out more transparent local environments. Webb is beginning to catch the consequences of that race in infrared light that has been stretched beyond previous limits of practical access. The phrase practical access matters because there is a temptation to talk as though earlier astronomers simply failed to look hard enough. That is not what happened. Every era of science is bounded by the instruments it can build and the wavelengths it can exploit. Hubble reached magnificently into the deep universe and transformed our picture of cosmic history. But there is a point where ancient light becomes so redshifted and the physically revealing features become so displaced that a new class of observatory becomes necessary. Webb is not correcting a lack of effort. It is correcting a lack of reach into the relevant transformed band. That difference deserves respect because it reveals how progress really works. We do not conquer ignorance by wanting less or more. We do it by building tools that meet reality where reality has moved. This theme repeats beautifully across the story of science. The bacterial world was there before microscopes. The radio sky existed before radio antennas. Exoplanet atmospheres were altering starlight before spectrographs became sensitive enough to detect their signatures. The early galaxies were radiating, enriching, and ionizing their surroundings before mid-infrared space astronomy could help us follow the most redshifted clues. Discovery often means not that something has appeared, but that we have finally developed the right interface with what was always already happening. Webb is a particularly dramatic interface because of how extreme the conditions are. Consider everything stacked against these observations. The source is unimaginably distant. The light is ancient. Expansion has stretched it far from its original wavelengths. Intervening matter affects what travels. The telescope itself must be prevented from overwhelming the signal with its own warmth. Even then, the observations have to be interpreted through calibration, modeling, and careful statistical judgment. Yet despite all of that, the result is not mere existence proof. It is physical insight. That is extraordinary in a very grounded way. A lot of modern discourse struggles with this kind of grounded extraordinariness. It tends to split into two bad modes. One is flat summary, which drains the human force out of the facts. The other is inflated language, which cheapens the facts by acting as if they need theatrical help. The reality of Webb lives in a better middle. The facts are enough on their own, if we are patient enough to let them expand inside us. A telescope in deep cold catches mid-infrared light from a galaxy seen less than 300 million years after the Big Bang. That light likely carries traces of intense early star formation and rapid enrichment. Another galaxy from a similar era appears to emit a line that should have had trouble escaping through the young universe's neutral hydrogen. This suggests local environments and early galaxy behavior more dynamic than many expected. Nothing about that is small. Nothing about it needs embellishment. The more honest the telling, the larger the feeling becomes. And the feeling is not just awe, there is a quiet tenderness in it too. Because these discoveries remind us that human knowledge is often an act of extending care into places we will never physically touch. We cannot go to these galaxies. We cannot stand inside their light at the moment of emission. We cannot watch the first stars in real time. But we can build an observatory that receives their altered afterglow and handle that afterglow carefully enough to reconstruct something true. There is restraint in that. Humility too. We take what the universe gives, altered though it is, and try not to force it into a story it does not support. That humility is one reason the script's deeper meaning keeps circling back to perception. The title seems to promise a story about a telescope exceeding a limit. It does deliver that. But underneath it is a broader statement. Reality often continues beyond the range of our current sensing, and progress comes from learning the form in which hidden truths still arrive. The early universe did not vanish, it redshifted. The information did not die, it migrated. Webb matters because it meets migration with design. Once you see that clearly, another line starts to take shape. Knowledge is not always about getting closer. Sometimes it is about becoming compatible. Compatible with the signal, compatible with the scale, compatible with the transformed shape of old light. Webb is compatibility turned into engineering. And in that engineering, a remarkable human fact becomes visible. We are a local species with non-local reach. Our bodies stay here, our instruments do not. Our senses are narrow, our methods widen them, our lives are short, our questions are not. That tension between brevity and reach may be the most moving thing in the whole story. Because every photon Webb records from cosmic dawn crosses a duration no human being can emotionally contain. It begins before Earth. It travels through epochs. It arrives while one set of observers is alive for a handful of decades. Yet within those decades, it is possible to detect it, analyze it, and place it inside a meaningful story of how the universe began making galaxies bright enough to matter. That is not victory over scale. It is cooperation with scale, and it is one of the rare places where intelligence feels equal to the strangeness of the world it inhabits. Equal to the strangeness, but never above it. That is important. The moment we start treating discoveries like these as proof that reality has been mastered, we lose the thing that makes them most beautiful. Webb does not finish the early universe. It does not dissolve mystery. It makes mystery more disciplined. It turns the blur into structure, the structure into questions, and the questions into something we can hold without pretending they are complete. That incompleteness is part of the living edge of the story. For all the progress now being made, we still do not possess a full census of the earliest galaxies. We still do not know how representative the brightest record holders are of the broader young population. We still have to work carefully through selection effects, through the tendency of extreme sources to announce themselves first, while quieter systems remain harder to characterize. We still have active debates about how rapidly some galaxies built up their stellar mass, how much dust could plausibly form so early, how strong certain emission lines should be under different conditions, and how exactly reionization unfolded across different scales of space. But notice what has happened to those uncertainties. They are no longer the uncertainties of emptiness. They are the uncertainties of contact. That is an entirely different atmosphere. It is the difference between wondering whether a continent exists and arguing about the shape of its coastline because ships have finally begun returning with maps. Webb is bringing back maps from a place that was not long ago mostly theoretical in emotional texture. We had equations, simulations, broad expectations, and fragments of evidence. Now we have galaxies with names, redshifts, line detections, and physical implications. The first substantial systems in cosmic history are becoming part of a geography rather than a rumour. And geography changes the imagination. When a realm becomes geographical, even in a scientific sense, you stop relating to it only through abstraction. It gains topography in the mind. The first galaxies are no longer just early. Some seem unusually bright. Some may sit in locally cleared bubbles. Some reveal shifted optical information in mid-infrared bands. Some suggest star formation and enrichment already underway at a surprising pace. These are not tiny adjustments to vocabulary. They are changes in texture. The young universe acquires weather. Weather is a good word here because it captures both pattern and instability. A weather system obeys physics without becoming simple. It can be modelled and still remain locally surprising. It can be smooth at one scale and turbulent at another. That may be closer to the opening universe than many of our older metaphors allowed. Not a uniform dawn gently rising everywhere, but a dynamic field of brightening pockets, obstructing gas, ionized clearings, fresh star formation, and uneven development, all taking place under the broader arc of cosmic expansion. This is why it would be a mistake to file Webb's achievements under better pictures of the early universe and leave it there. Better pictures are part of the story, and they matter deeply for public imagination. But the stronger truth is that the telescope is altering the conceptual weather of cosmology. It is making the dawn of galaxies feel less like a symbolic beginning, and more like a physically varied regime whose internal differences now matter. The universe is becoming less like an outline and more like terrain. Terrain produces a new kind of humility. When everything is abstract, humility can become theatrical. We say the universe is vast. We say we are small. These lines are true, but they are often too smooth to do real work. Specificity humbles much better. It is one thing to say the cosmos is beyond us. It is another to understand that visible light features from the first substantial galaxies can be stretched so far by expansion that only a cryogenic instrument operating in deep infrared can catch the resulting signal, and that even then the interpretation depends on painstaking care. That kind of humility has structure. It does not flatten us into insignificance. It reminds us what kind of effort reality actually demands. And effort is written all through this story. A large mirror folded for launch and then unfolded in space. A sunshield the size of a tennis court deployed with extraordinary precision. Instrument temperatures driven down so low that the observatory would not overwhelm the faint infrared whispers it was built to hear. Survey teams searching deep fields for candidates. Spectroscopic confirmation separating the genuine frontier from the merely suggestive. Mid-infrared detections opening another layer of interpretation. Theories revised, argued over, improved. None of this is glamorous in the cheap sense. All of it is glorious in the serious one. Because serious glory comes from alignment, from getting many difficult things right at once. That alignment is what makes a sentence like this possible. A species that cannot naturally see infrared has built an observatory that can detect and begin interpreting mid-infrared signals from galaxies seen less than 300 million years after the Big Bang. The sentence sounds almost too large to fit inside one mind, but it is not exaggerated. It is simply the current state of the world. Sometimes that is the strongest line available. The current state of the world. The current state of the world is that we now inhabit a civilization capable of receiving transformed light from the opening chapter of galaxy history. The current state of the world is that early galaxies once expected to be mostly beyond practical physical interpretation are beginning to reveal internal conditions. The current state of the world is that cosmic dawn has moved from generalized awe toward textured evidence. That is not a future promise. It is where we are. And where we are alters the meaning of where we came from. When people hear about the early universe, they often place it at a conceptual distance so great that it feels disconnected from ordinary reality. Something for cosmologists, not for the rest of us. Something too remote to matter emotionally except as a source of occasional wonder. But the first galaxies are part of the same continuous history that eventually produces the Milky Way, the Sun, the Earth, continents, weather, metabolism, memory, and language. Not in a simplistic "we are made of stars" slogan sense, but in the hard material sense that the universe had to begin building structure and chemical complexity somewhere. Webb is letting us watch that process much closer to its beginning than ever before. That does not make the first galaxies our ancestors in any tidy narrative way, but it does place them on our side of the same unfolding. They belong to the chain that leads to later complexity, and the more rapidly some of them seem to have become bright, active, and chemically interesting, the more intense that chain looks in its opening links. Intensity is the word that keeps returning. The early universe was intense in density, in radiation, in transformation, in consequence. Webb is showing us that with increasing precision, it is not proving that every old expectation was wrong. It is proving that some old expectations were too emotionally mild. The beginning was not only simple and sparse, in places, it was already forceful. That is why the detections feel like more than measurements. They feel like a correction to tempo. Tempo matters because it shapes meaning. A slow beginning suggests one kind of universe. A beginning where significant structure and energetic processes appear surprisingly early suggests another. Not another universe, but another emotional understanding of the same one. One where reality wastes less time than we imagined. One where matter under the right conditions becomes consequential with remarkable speed. One where the first substantial galaxies are not just markers on a timeline, but engines already changing their surroundings. And once that view takes hold, the title reveals its deepest force. James Webb just recorded infrared light beyond previous limits is not only a statement about a technical milestone, it is a statement about threshold contact with a more active beginning than many people had truly felt before. The infrared is not incidental. It is the transformed form in which that beginning reaches us now. The previous limits are not mere numbers. They are old boundaries of compatibility between our instruments and the altered state of ancient light. Crossing them means the earliest galaxies can begin to emerge as physically thick realities rather than remote abstractions. There is a quiet emotional consequence to that. The ordinary sky becomes less ordinary forever. Not because every person now has to think in redshift and line emission every time they look up, but because the simple visual scene overhead can no longer be mistaken for the whole of what is there. Above the familiar constellations, beyond the visible points, beyond the darkness our eyes interpret as empty, there is an archive of transformed light still arriving. Some of it began its journey before our planet existed. Some of it carries evidence of the first substantial galaxies already burning, enriching, and reshaping their local worlds. And now, at last, some of that evidence is being caught in the deeper infrared where it had migrated all along. That realization does not need to be loud. In fact, it lands best when it is quiet. A frozen telescope hangs in space. A photon stretched across 13.5 billion years enters a detector. A pattern survives analysis. A galaxy from cosmic dawn becomes a little less anonymous. The beginning becomes a little less hidden. And somewhere, without fanfare, human perception grows wider than it was before. Wider, and with that widening comes a strange kind of peace. Not the peace of having everything explained, the peace of realizing that explanation can keep deepening without draining the world of wonder. In fact, with Webb, the opposite has happened. The better the measurements become, the more vivid the early universe feels. It is no longer a decorative backdrop for philosophical reflection. It is a physically active era with gradients, feedback, local victories over opacity, and galaxies already producing enough internal drama to leave behind readable signatures after almost the entire history of the cosmos has passed. That is an extraordinary sentence to be able to say plainly. Readable signatures after almost the entire history of the cosmos has passed. The phrase contains nearly the whole emotional structure of the story. Something happened long ago. The universe expanded. The light stretched. Some of its crucial features slipped out of the visible domain and beyond older practical limits. A telescope was built to meet that altered signal where it now lives. It recorded the light, held onto the pattern, and gave us back not just distance but condition. Not just existence, but process. Not just a frontier, but an atmosphere. Once you feel that, even the technical language starts to soften into something more human. Redshift stops sounding like jargon and starts sounding like time made visible. Mid-infrared stops sounding like a niche band on an instrument brochure and starts sounding like the place where ancient visible truths have gone. Spectroscopy stops sounding like a specialist tool and starts sounding like the art of not being fooled by a pretty image. Every term regains its purpose. And purpose is the difference between information and memory. A culture can drown in information and still remain shallow. Facts alone do not guarantee understanding. What creates understanding is arrangement, consequence, pressure. Webb's discoveries matter because they arrange facts into a changed perception of beginnings. The first substantial galaxies were not just marginally earlier than expected. Some were active enough, bright enough, and physically interpretable enough to reveal that the opening universe was already generating complexity at a pace that feels more urgent than older intuition allowed. That is a memory-forming truth. It changes how the mind stores the cosmos. The cosmos becomes less like a sequence of textbook milestones and more like a living escalation. First, neutral hydrogen fills space, making the young universe difficult for certain light to cross. Then local sources begin to ignite. Then radiation starts clearing pockets. Then galaxies do not merely exist but become bright enough to alter their surroundings and leave behind chemical traces. Then the light from those systems stretches outward for billions of years until it arrives in a form no human eye could ever naturally read. Then, very late in the story, a species arrives that can. That late arrival is one of the quiet emotional centers of everything. We are so late, so impossibly late. The photons Webb records from cosmic dawn began their journey before the Earth formed, before the sun, before any living membrane or nervous system or eye. They crossed epochs indifferent to whether anyone would ever be waiting at the other end. And yet here we are. Not because the universe was aiming for us, not because the story was secretly arranged around our existence, simply because one branch of matter became conscious enough, technical enough, and patient enough to receive what was still coming. There is grandeur in that, but it is not cheap grandeur. It is earned by improbability. A species on a rocky world around an ordinary star learns mathematics, optics, thermodynamics, cryogenic engineering, orbital mechanics, detector physics, signal processing, and enough astrophysics to infer the state of galaxies from transformed light, arriving 13.5 billion years late. If you say that too quickly, it sounds like a slogan. If you say it slowly, it becomes almost difficult to believe. Yet this is now an ordinary fact of the world. Papers are written, datasets are archived. Models are updated. Somewhere, quietly, a civilization has begun to read deeper into the first few 100 million years than any civilization ever has. And the reading is not passive, it changes the reader. That is true of all real knowledge, but it becomes especially visible here because the subject is so much larger than the mind taking it in. Once you understand that the earliest galaxies are reaching us in altered light, that some of their most informative features have migrated into infrared bands beyond previous limits, and that Webb was built precisely to follow that migration, then ordinary sight stops feeling final. Vision becomes one narrow solution among many possible ways of being informed by the world. Human perception starts to seem less like a finished gift, and more like a local beginning that instruments can extend. This is one reason the story feels bigger than astronomy while remaining fully grounded in astronomy. It is a story about compatibility with reality, about the fact that the world often exceeds us not only in scale, but in format. The truth may be there, intact in some lawful sense, while remaining inaccessible because we are listening in the wrong register. Webb is powerful because it changes the register. It does not force the universe to simplify. It adapts us to complexity. That adaptation is visible in the way the frontier now behaves. A new candidate is found. Caution surrounds it. Follow-up narrows uncertainty. The redshift is secured. A longer wavelength detection changes what can be physically inferred. A once remote object becomes a site of real argument about star formation, gas conditions, enrichment, and surrounding opacity. Then another object appears, and another, and the edge of the map starts to look less like a single point and more like a coast. A coast is a beautiful image for this phase of science because it captures exactly the mixture of knowledge and incompleteness we now inhabit. We have reached land, but only parts of the shoreline are charted. We know enough to say the continent is there. We know enough to see ridges, inlets, weather systems, local surprises. We do not yet know the full interior. The right response is neither doubt nor triumph. It is sustained attention. Sustained attention may be the hidden hero of the whole Webb era. It is easy to celebrate brilliance, harder to appreciate steadiness. Yet steadiness is what allows discoveries like this to remain trustworthy. There is steadiness in the instrument, maintaining its thermal discipline in space, steadiness in the observers, gathering deep exposures, steadiness in the analysts, resisting premature conclusions, steadiness in the scientific culture that values confirmation over excitement when the claim is large. The result is a kind of accumulated credibility that lets genuinely astonishing facts enter the world without having to disguise themselves as hype. That matters now more than ever, because the discoveries themselves are enough to overwhelm intuition. The first few 100 million years are no longer a mostly silent corridor at the edge of theory. They are becoming a populated interval of cosmic history. Not densely populated in the way the later universe is, of course, but populated enough with substantial energetic systems to force a richer account of how quickly light, structure, and chemistry became consequential. That is a major shift in perception, and it arrives not as spectacle but as measured light. Measured light, that phrase has a dignity to it. The universe sends out radiance. Instruments receive it. Methods measure it. Meaning follows. Strip away all the surrounding noise, and that is the core of the human achievement here. We do not command the cosmos. We measure the light. We do not possess the beginning. We receive what remains of it. We do not abolish distance. We learn to read across it. Every one of those limitations makes the result more moving, not less. Because movement comes from resistance, a story with no resistance is weightless. Webb's story is full of resistance, thermal, optical, cosmological, interpretive, temporal. Ancient light resists our senses. Expansion resists direct intuition. The early universe resists easy storytelling. Yet the resistance is not absolute. It yields to the right kind of care. And when it yields, even slightly, the effect is profound. A galaxy from cosmic dawn stops being a hypothetical opening note and becomes a measurable system with internal force. That is the threshold we are living inside right now. The beginning is no longer only something we infer in broad strokes. It is starting to answer in specifics. Infrared light stretched beyond previous limits is now carrying back pieces of a reality that used to lie just outside practical access. And because of that, the first substantial galaxies no longer feel like distant ceremonial ancestors of later history. They feel present in a different way, still remote, still transformed, but finally readable enough to remind us that the universe began becoming vivid, long before there was anyone here to see it. Long before there was anyone here to see it, and that may be the final perception change this whole journey has been moving toward. We spend so much of life inside immediacy that we begin to mistake immediacy for reality itself. What arrives now feels real. What can be seen now feels available. What fits the scale of the body feels true in the deepest way. Webb has been undoing that illusion with extraordinary gentleness. It has shown us that some of the most revealing parts of cosmic history do not arrive in the forms our bodies prefer, and yet they are no less real for that. They come stretched, delayed, filtered, shifted into deeper infrared, and if we are careful enough, they can still be read. That is the meaning hidden inside the title. Not simply that Webb went beyond previous limits, though it did. Not simply that it recorded infrared light, though it did that too. The deeper truth is that previous limits were limits of compatibility between our tools and the transformed state of ancient light. The universe had not withheld its past. Its past had moved. Webb is powerful because it meets that movement without asking reality to simplify itself for us. Once you understand that, the story stops being about a telescope alone and becomes a story about maturity and knowledge. Childish knowledge wants truth to arrive in familiar colours. Mature knowledge learns to recognise truth after distance has altered its form. That is exactly what is happening here. Ancient galaxies sent out light in one state. Expanding space translated that light into another. Human beings built an instrument suited to the translation. And in doing so, we crossed from admiring the edge of cosmic dawn to beginning to study its internal weather. That weather is what lingers. The first substantial galaxies now feel less like ceremonial first lights, and more like active places in a patchy young universe. Some were already bright enough to stand out against expectation. Some appear to have formed stars intensely enough to leave strong internal signatures. Some may already have enriched their gas surprisingly quickly. Some seem able to help clear, or inhabit, local regions where difficult radiation could escape through a wider sea of the neutral hydrogen. This is not a blank beginning. It is a beginning with gradients, pressure, and uneven acceleration. The universe did not wait to become interesting. That line matters because it corrects something quiet but persistent in the human imagination. We often assume that the beginning of any large process must look simple from the inside. Webb is reminding us that beginnings can be ferocious with possibility. Under the right conditions, matter does not need to hesitate into consequence. It can organize, ignite, enrich, and begin reshaping its environment astonishingly early. What looked, from a great conceptual distance, like a gentle dawn now looks more like a scattered ignition. And yet the feeling left at the end is not violence, it is witness. Because what finally overwhelms you is not just the speed of early structure or the elegance of the instrument, it is the sheer fact of contact. A photon leaves a galaxy less than 300 million years after the Big Bang. It begins its passage before the Earth exists, before the Sun, before any creature has eyes. It crosses a universe that keeps expanding under it, stretching it out of the visible range and into deeper infrared. It survives. It reaches a frozen telescope hanging in darkness. A detector records it. Analysis extracts its pattern, and from that pattern, across 13.5 billion years, a species that was nowhere in the scene reconstructs a little piece of what happened there. This is what knowledge looks like at its most beautiful. Not domination, not conquest. Contact across transformation. There is a reason that lands so deeply. Most of our lives are spent confronting forms of distance we cannot bridge. Distance in time, distance between minds, distance between what we want to know and what we can presently prove. Webb does not solve that human condition, but it offers a rare example of distance yielding, not because the gap was small, but because the method was worthy of it. That may be why the whole story feels so calm despite its scale. It is a story of immense separation answered by precision rather than force. Precision is one of the great moral tones of science when it is healthy. A hot telescope would have flooded the signal, a smaller mirror would have caught too little, narrower wavelength coverage would have let key information slip by, less cautious interpretation would have turned surprise into noise. Instead, the opposite happened. The instrument was built to the problem, the observations were checked, the claims were tightened, and the result is a frontier that feels trustworthy enough to expand your sense of reality without requiring you to suspend judgment. That is rare. It is one reason Webb has become more than a machine in the public imagination. It stands for a kind of seriousness we still hunger for, the possibility that the world can become larger and stranger without becoming less intelligible, the possibility that wonder and rigor do not compete, the possibility that even the earliest galaxies can move from distant legend into evidence without losing any of their awe. If anything, the awe becomes cleaner. Cleaner because it no longer depends on vague language about the universe being big and mysterious. We already knew it was big. What we did not know, not in this felt way, was that some of the oldest visible truths of early galaxies would have to be pursued into deeper infrared bands than previous astronomy could fully exploit, and that once pursued there, they would reveal a beginning more active and more readable than many had imagined. That is not generic wonder. That is specific wonder. It stays longer because it has bones. And now it changes the ordinary. The next time you see the night sky, it may still look exactly as it always did. A few stars if you're near a city, a river of faint light if you're far from one, darkness between points, silence overhead. But the simplicity will be harder to believe in. You will know that hidden in that darkness is an archive of altered messages. You will know that some of the earlier substantial galaxies in cosmic history are still reaching us, not in their original colours, but in stretched infrared forms that only very recently became readable. You will know that the sky is not merely what appears to the eye, it is what survives, what migrates, and what patient minds learn to receive. That knowledge does something subtle to a person. It does not make daily life smaller, it makes daily life more improbable. The room you sit in, the body you inhabit, the brief life through which you experience anything at all, these things begin to stand against a larger background without losing their intimacy. We are small, yes, but not too small to witness, not too small to build instruments that extend us into the deep past, not too small to understand that reality is often present long before it becomes visible in a form we can trust. Maybe that is the final gift of Webb's latest achievement. It reminds us that invisibility is not emptiness, silence is not absence, distance is not disappearance. Sometimes the truth is still coming, stretched into another register, waiting for the right reader. And now, for the first time in history, we are becoming that reader for some of the oldest galaxies the universe ever made.